This is section 7.2, and we're now going to begin looking at the truly new techniques for integration that aren't just kind of variations on things that you've seen before. One of the things that we learned when we first learned to do antiderivatives was that there's no such thing as a product or quotient rule for antiderivatives, and that's true. This next technique, however, is a technique that may help us when we see integrands that are products. Here's how it works. I'm going to start. This technique, by the way, is called integration by parts, and it's actually based on the formula for the derivative of the product. If you remember, this is our product rule, right? The derivative of u times v is u times v prime plus v times u prime. We often did it with f's and g's before, but same thing, just different letters. What we're going to do is we're going to integrate both sides of this equation with respect to x. So I'm going to put an integral on the left-hand side with respect to x. So notice the integral dx is equal to the integral on the right-hand side. Again, with respect to x. That's that dx. The dx's here, in some sense, cancel out. It's not truly a fraction, but for our purposes here, we can treat it like one. And so when you kind of imagine those canceling out, you end up with d uv, the differential of uv. And on this side, I'm imagining, again, I'm treating the dx algebraically like a differential. Imagine distributing it. It would cancel out the dx's in both denominators. And so I'm going to write this as the integral of u dv, plus I'm going to separate and write the integral of v du. Right, again, the dx's have all canceled out. All right, on the left-hand side, the integral and the differential are inverses. Right? When you both take the derivative and the integral of something, they basically gets you back to where you started from. So they essentially cancel one another out as well. And I just end up with uv equals the integral of u dv plus the integral of v du. Although it doesn't really matter which one I leave on one side and which one I take to the other, the classic way you usually see this written is to leave the u dv on this side and subtract the second integral over to the left. What this does for us is give us a formula that says if we've got a product of two things, something that we'll call u and something that we'll call dv, we can use this formula to find the antiderivative. Now notice, it's not a golden ticket or anything like that. We still have an integral to do. But sometimes we can make our integral simpler using this technique. So this formula right here is the formula for integration by parts. And it's actually written for you on the top of your next page. In a nice formal way. Get it over here. There we go. So as long as u and v are functions of x with continuous derivatives, this is true. In order to make use of this formula, we're always going to have to make a choice of u and dv. And that's going to be the kind of experience part of this technique. The more of these you do, the better you'll get at choosing your u and your dv. But if you've got an integral with a product in it, what you'll want to do is pick part of it to be u and pick the other part of it to be dv. Every factor has to go into either the u or the dv. It all has to be there somewhere. Right? Again, the more you do, the better you'll get. But here's a couple of general kind of tricks, if you will, or tips maybe is a better word. One thing to keep in mind is you are going to have to integrate the v. So try letting dv be the most complicated part of the integrand that does fit a basic integration rule. U then will be the rest of it. So let dv be something you already know how to integrate. Another sort of general idea to keep in mind, we're going to have to take the derivative of u as part of our process. So try letting u be the part of the integrand whose derivative is simpler than the function itself. And then dv is whatever's left over. We'll try a few of these, and I think you'll see that the more we do, the more you'll kind of catch on to the u's and the dv's. So here's my first integral, the integral of x times cosine x dx. Definitely see a product here. I need to pick a u and a dv. The dx will always go with the dv, so that part's easy. But then between the x and the cosine x, I'm going to put one of them here with the u, and I'm going to put the other one with the dv. And I've got to decide which is which. Now in this case, both of my tips help. Notice that x gets simpler when you take its derivative. Cosine x doesn't. So letting u be x fits that tip number 2. Additionally, it says let dv be the most complicated part that we know how to integrate. And I know how to integrate cosine x, and that's more complicated than just x. So letting dv be cosine x dx is a good choice. All right. Notice I've got everything. X, cosine x dx, it's all there in my u and my dv. All right. Ultimately, we need u, v, du, and dv. We need them all. So knowing u, I can get du just by taking the derivative. It would just be 1 dx, or just plain dx. I can get v by taking the integral of this, and the integral of cosine x dx is sine x. I won't bother with the plus c here. When I'm completely finished with the entire antiderivative, I'll put the plus c in the end. All right, we're ready to set up our integration by parts. According to the formula, again, just look up at the top of the page. I should have uv minus the integral of v du. So u times v, x times sine x, minus the integral of v du, v is sine x, du is just 1 dx. And notice that this did what we wanted it to do. We still have an integral, but now it's a much easier integral to do. The integral of sine x dx is actually negative cosine, so negative negative is going to make that a plus cosine x, and now I'll put my constant of integration on here at the end. All right, so there's our first integration by parts. We'll do several more examples, just to kind of help you get used to this. The next problem, example 2, we'd like to find the antiderivative of natural log x dx. Now I did say that we typically use these for products, but in this case you're probably not seeing a product. I'll show you how to deal with that. Not an antiderivative that we know right off the bat, so I'm going to try integration by parts, choosing a u and a dv. The dx has to go with the dv, that's a given. But then as far as what to do with the rest, well, I don't know how to integrate ln x, so I can't put it here with the dv. I have to put it with the u. And that means dv is just dx, or if you want to put a 1 dx there, you certainly can. Notice again, if I multiply this all together, I have everything. All right, du, the derivative of ln x is 1 over x dx. V, the integral, if I just integrate both sides here, the integral of 1 dx is x. Ready to set up my integration by parts. uv minus the integral of v du. uv, x times ln x, minus the integral of v, which is x, times du, 1 over x dx. All right, really nice here. Those x's, of course, simply cancel out, and I just integrate 1. And so I get x ln x minus x plus the constant of integration. By the way, I won't take the time to do it here on the video, but I would encourage you, for any of these, go back and take the derivative of this and verify that you really do get ln x. You should, and that'll kind of prove to you that it's actually working. All right, let's go ahead and try the next one. All right. Sorry, a little technical difficulty there. All right, here we go. Next problem. We would like to integrate x e to the 3x dx. Once again, my first job is to figure out the u and the dv. I do know, just like before, x gets a lot simpler when I take its derivative, so I really like using x or a power of x as my u. And I do know how to integrate e to the 3x dx, so let's let that be our dv. Du will just be 1 dx. And integrating this, technically there's a little u substitution in here, right? U would be equal to 3x, but we've seen these so many times. Have you started to recognize that all that happens is you end up bringing that 3 out as a 1/3 outside the integral? I'm hoping so. I'm going to start using that shortcut. I'll get 1/3 e to the 3x. Notice when you take the derivative, you'd get 1/3 e to the 3x times 3, and the 3's would cancel. So that has to be correct. All right, integration by parts. uv, multiplying these together, 1/3 x e to the 3x, minus the integral of v du, 1/3 e to the 3x times dx. So I have my 1/3 x e to the 3x minus, I'm going to bring this 1/3 out here. And then notice when I integrate this, it's the exact same thing we integrated by before. I'll get another 1/3 e to the 3x plus our constant of integration. So I end up with 1/3 x e to the 3x minus 1/9 e to the 3x plus c. All right, example 4. Back to my choosing a u and a dv. This time I'm not real excited about letting the square root of x be my u. When I take the derivative, I get 1/2 x to the negative 1/2. That definitely does not get simpler. But notice if I let my u be ln x, the derivative is 1 over x, which is easier to work with than the natural log. So I'm going to use u equal ln x this time. It gets simpler when I take its derivative. dv will be the square root of x dx. So my du is indeed 1 over x. And then integrating, v would be, see that's x to the 1/2, so x to the 3/2. Instead of dividing by 3/2, I'm going to multiply by 2/3. And then I'll do my integration by parts formula. u times v, 2/3 x to the 3/2, ln x, minus the integral of v du, 2/3 x to the 3/2. I'm sorry, when I did the du here, I forgot the dx, didn't I? Let me put that in right now. There's my v. My du would be a times 1 over x dx. So let's see, I'm going to pull the 2/3 out in front of the integral. And then that's an x to the first, so if I subtract those exponents, that's just x to the 1/2 inside my integral. And that's not too tough to integrate. Integral of x to the 1/2, again, is x to the 3/2 multiplied by 2/3. And there's my constant of integration. So when all is said and done, I've got 2/3 x to the 3/2 natural log x minus 4/9 x to the 3/2 plus c. All right, so if you're starting to get a little bit of a feel for this, let's look at some situations where maybe we have to be a little bit more creative. Here in example 5, I've got the integral of x cubed over the square root of 4 plus x squared. Now typically, when we have something under a radical, we like it to be the u, right, in a standard normal u substitution. I know that's not going to work out this time, but I want to kind of think ahead in terms of what would have to be on top if this was going to be integrable, right? If that were my u, the derivative would be 2x, so I would actually need an x to the first on top. I'm going to capitalize on that, see what I can make of it. I could integrate this with a standard normal substitution if only I had just x to the first on top. So I'm going to go ahead and do that. When I integrate this, I know what I'm going to do. Now I really had x cubed here, so the extra x squared is what becomes my u. Okay? A little bit more creative than the last choices that we've had to make. All right, du, just 2x dx. To integrate to get dv, I'm going to have to use a little bit of a substitution here. Let me see if I can squeeze it in. Since we're using u for something else, I'm going to call my substitution w this time. If I now let w be what's under my radical, 4 plus x squared, then dw would be 2x dx. And I could take that 2 and move it to the other side. So x dx would become dw, 1/2 dw. And I have that right there. So I'd have 1 over the square root of u, or w, excuse me. And then the x dx, I'll make that a 1/2 dw. So I have 1/2. Let's see, that's really w to the negative 1/2. So power rule would give me w to the positive 1/2 divided by 1/2. Those 1/2s will cancel, meaning v is just really the square root of my w, which is 4 plus x squared. All right, a little more work to get the v this time. Well, let's see what we got. We've got uv minus the integral of v du. uv will be x squared, square root of 4 plus x squared, minus the integral of v du. That'll be a 2x square root 4 plus x squared. Dx. All right, this part's done. And that's not just a standard integral, but notice we could actually borrow our same substitution with the w here if we let w be what's under that radical, the 2x dx was actually the dw even before I brought the 1/2 over, right? So let's do that. Let's call that the square root of w. And then this whole 2x dx. 2x dx was just equal to dw. All right, that's w to the 1/2. So antiderivative would be w to the 3/2 times 2/3. And the only thing that's left to do is to put back the w. There we go. So always looking to make that dv something that you know how to integrate, even if your choice has to be a little bit creative. All right, in the next example, it says sometimes we just have to be persistent. What do we mean by that? Well, let's get started and see what happens. Pick a u and a dv. X squared certainly gets simpler. It becomes 2x when I take its derivative, so I'm going to let u be x squared. And that leaves the e to the x dx, which I certainly know how to integrate, to be my dv. du then is 2x dx. And integrating over here, v is just e to the x. So integration by parts, uv, x squared, e to the x, minus the integral of v du, that would be 2x e to the x dx. All right, looking at this, we still have a product. And this is what I mean by being persistent. We're going to need to do another integration by parts in order to figure this integral out. So let's do it again. We already have the x squared e to the x. We're done with that. And now we're going to subtract this whole result. This time, I'm going to use the 2x as my u, and my dv is still going to be e to the x dx. du will be 2 dx, and v is e to the x again. So I'm going to go ahead and do this formula again. uv, 2x e to the x, minus the integral of v du, 2 e to the x dx. All right, I got a minus 2x e to the x, and minus a minus there is going to be a plus. The integral of 2 e to the x is 2 e to the x. And there's my constant of integration, and we finally got there. So we had to do a double integration by parts, and I will warn you, it's not uncommon. The higher the power here, the more times you may have to run integration by parts. Notice each derivative knocks the power down by 1. So if horror of horrors, I had started out with like an x to the 8th here, I would have had to have done integration by parts 8 times before I finally would have come up with something that I was able to integrate. All right, example 7. It's kind of an interesting one. We have to be persistent on this one, but actually there's also a little bit of creativity involved as well. So I've got my integrand as e to the x cosine x dx, and I have to pick a u and a dv. And actually, just because we're going to have to do this more than once, I'm going to color code here. like I usually do. All right. In this case, I would argue that neither function is obvious as far as being the u. The derivative of e to the x is still e to the x, doesn't get any simpler. The derivative of cosine x is negative sine x, doesn't get any simpler. I know how to integrate both e to the x and cosine x, so it really doesn't matter in this case, and it turns out it truly doesn't. You can pick it either way. I'm going to choose u to be e to the x and dv to be cosine x dx, but it turns out it would work the other way also. All right, the derivative for du is still e to the x. Bring the dx over. And the integral of cosine x is sine x. So I've got my uv minus the integral of v du would be e to the x sine x minus the integral of v du would be sine x, e to the x dx. I'm going to write that as e to the x sine x dx. So that part is obviously done. But I now have another product here, which lends itself again to integration by parts. Well, doing it twice worked out pretty well for us last time. Let's try it again. I'll let, once again, u be e to the x. And this time the dv is going to be sine x dx. So du is e to the x dx. And integrating here, v is negative cosine x. So I've got e to the x sine x minus all of this, and I'm going to do my uv minus v du now. uv, negative e to the x cosine x, minus the integral of v du, negative e to the x, sorry, these two, negative e to the x cos x dx. All right, let's see here. I'm going to go ahead and do a couple of things. I'm going to distribute this minus sign first of all, because there's an awful lot of negatives hanging around here. That'll be a plus e to the x cosine x, and a plus, no, excuse me, that's going to be a minus, isn't it? There's a minus, minus, minus. 3 negatives is going to make that a minus. The integral of e to the x cosine x dx. All right, what I hope you're beginning to see is this is almost like an endless loop, right? What we have here is actually right back to what we started with. So if I were to do another round, do another u and a v, this would just keep on repeating itself. It would keep on cycling over and over. And I would never get to a final answer by continuing to integrate by parts. What I can do, however, and this is where the creativity comes in, is a little algebra. At this stage, I'm going to say that what I have here is the value of this original integral, right? This is equal to all of this. So I'm just going to say this is equal to the original integral because that's what I've been trying to work out this whole time. Well, those are like terms, aren't they? So if I were to add this over to the other side, I'd have 2 of them. And now, to find the value of the integral that I really wanted in the first place, all I got to do is divide by the 2. And And there's my final answer. Okay. All right. Lastly, I just want to mention that we can also do definite integrals using integration by parts. So we'll finish up with this last example. The integrand is x sine 2x dx. And by now you've probably seen these often enough to recognize that when you have a multiplier of x or x squared, that's almost always going to be your u. dv will be sine 2x dx. So du, the derivative, is just 1 dx. And integrating here, the integral of sine is a negative cosine. And there would have been a little tiny u substitution here, right? U would have been equal to 2x. Derivative would have been 2, which you'd have then divided to the other side. And that would have given us a 1/2. Again, you can write out those little bitty u substitutions, but we do them so often that I'm hoping you're kind of starting to get a feel for those enough to just sort of make that adjustment when it's just a constant. All right, so here we go. uv, negative 1/2 x, cosine 2x, minus the integral of v du, negative 1/2 cos 2x, and then just dx. It's negative 1/2 cos 2x. And of course, those two negatives just become a positive, so I have a plus 1/2 times the integral of cosine 2x. Same argument, the integral of cos 2x would be sine 2x. But once again, the u substitution would bring a 1/2 out here. So this is that 1/2. This is the new 1/2 that comes from the integral. And all of this gets evaluated from 0 to pi halves. So I'm going to have, let's see, negative 1/2 times pi halves. Cosine 2 times pi halves would just be pi. Plus, that'll be a 1/4 sine pi. Subtract. When I plug a 0 in here, that x is just going to give that multiplier of 0 to that whole first term. And then I'll have a plus 1/4 sine 0. So I have a negative pi fourths. Cosine of pi is negative 1. Plus 1/4 sine of pi is 0. And then a minus 1/4 sine of 0 is 0. So I just end up with a positive pi fourths here. All right, that brings us to the end of section 7.2, integration by parts.